most protocols have, most blockchain protocols, I think all blockchain protocols, have strong coherency, with the exception of the sharded or multi-chain protocols, which have very weak coherency. In general, if we look at systems, I mean, feel free to shout something that counterexample, but from what I can tell, and everyone that I've talked to has not been able to give me a counterexample. I don't know if there is like a principle behind this that is, and someone once told me that there was, but then they didn't tell me what the name was. But as far as I can tell, there is an antagonism, like a very general antagonism throughout systems, any systems, whether they be IT systems or biological systems or social systems, between size and synchrony. And we can think of synchrony essentially as being coherence. So essentially, the bigger a system gets, the less coherent it gets. But in order to scale a system, it has to become bigger. Which means to scale a system, you kind of have to put up with a resultant lack of coherence. Otherwise, it's going to break and slow. Like maybe it's going to become less secure, maybe less resilient, whatever. But like, in order to scale a system, keep all the other properties equal, it's going to result in less synchronous behavior and as such a greater level of incoherence. And this is something that we found with Polkadot, right? Being the first blockchain to shard. The assumption was that, oh, well, you just shard it into multiple blockchains and you can keep the security and it's just going to scale. Right? It's just going to be fine, it'll just scale and it'll all be good. But in reality, scaling through having, through sharding, the system, state, partitioning, if we're being technical about it, that's what sharding is problematic because it introduces this lack of coherency. What one shard doesn't affect the other shards until there is some sort of like message transfer, some transfer of information between the shards. And unless this transfer of information is incredibly fast and high bandwidth, which it's not, then you have a problem because your system becomes very incoherent quite fast. And as we see, other blockchains rushing to their persistent state partitioned model of scalability, at least the ones that are not scaling in an ultra centralized way. And they're each going to start running into this problematic antagonism where things that used to be possible because everything happened in a synchronous manner become a lot harder to do. You can say, oh, well, you sequence in a synchronous manner and then validate in a parallelized manner. And this can paper over the crack. But the problem is that firstly, you end up with a high degree of centralization for this sequencing. Secondly, it's because it's very intensive. You essentially have to run. You have to have total knowledge of all of the different partitioned pieces of state. So the node that is sequencing basically doesn't scale because they have to know everything about everyone. Yeah, and this is precisely what we don't want to have to do. In reality, that will work okay for maybe doing 2 or 3 shards, but as soon as you want to do hundreds of shards, it doesn't really make any sense. You need some other way of managing this partition. Good. So, where does Jam come in? I'm not going to go too much into the Jam approach because I think everyone here probably is already fairly knowledgeable about the fact that there is a grey paper, which is the spec, and the fact that there is a Jam prize, and the fact that there is this toaster. Anyone not know about this?
What's the latest on the Jam toaster?
So it's the first consignment is being delivered in the first few days of November. Apparently, the main issue is Portugal. And Portugal's inability to import goods from non-EU countries, and Parity had to set up some really sophisticated import structure to be able to get these, because these machines are made in Taiwan, right? And they had to set up some crazy legal structure.
And I was concerned they were worried that you're going to take the grid off, the electricity grid.
Take down Lisbon.
No. We actually have a really good supply of electricity to the palace. We've got like 300 kilowatts. So yeah, electricity-wise, we should be good. But yeah, the import is like a big headache. But I think, as I understand it, from the 1st of November, Parity will have this structure going, and then the customs guys should be okay with it. So it's the first, I think, 20 or 30 nodes have been made. Like they're physically there now. They're just waiting shipment until we have all the paperwork sorted. Then the following, I think for phase 1, it's 77 or 87 nodes. So the other, whatever, 50 or 60 will be delivered, will be made over the following month and then delivered by the end of the year. So yeah, we should have an up and running toaster roughly December. And we'll probably have quite a large portion of it already running mid-November. I have a picture. I actually shared it in the last fellowship call. Yeah, it's fun. I've got another picture on here, which I'll bring up in a second. Right, so yeah, you all know about the Jam Prize, 5 milestones, importer, authorer, half-speed, full-speed, and secure nodes. And there's a bunch of other things, a sort of fast route into the fellowship, audits paid for by the time you get to milestone 5, and we'll do some seminars, of which I suppose the first one will be Thailand in 3 weeks. Hardware, which I think kind of aiming to be at milestone 2, 3 time, and then toaster access. I think everyone knows all the languages. These are the languages that we're sort of pushing to have implementations in. Here is a picture of the toaster node. It's got a little logo on. And I think these are all, I think we're running 96 core machines, with the idea that in the first iteration of the toaster there's about 85 of them, and then in the second iteration there's 170. So we kind of double it. Initially we're doing 6 cores per node, and then eventually we'll do 12 cores per node. Yeah, good. Right, let's move on to the protocol itself. So, yeah, going back to the password, Polkadot. We got this persistent state partitioning, which is basically parachains have their own state. They move forward independently. They send messages via XCM, XCMP, or in more recently IXM. Building your own chain is not a trivial undertaking. It contributes to some of the high barriers to entry compared to, for example, deploying a smart contract. So we have, I would say the bigger issue here is the persistent state partitioning, essentially because it makes interoperability harder. Right? It makes synchronous composition very difficult. Essentially impossible, like at the moment. In principle, in the future, it could be possible with like some cunning shared sequencing and maybe like something like Spree, but Spree kind of requires Jam. Okay, we move to Ethereum, particularly Ethereum's future roadmap. It's already clear it's pretty costly to run things on the L1. L2s are a little bit cheaper now, particularly with one of the recent upgrades. Getting messages between L2s is incredibly slow, mostly because they use different inefficient forms of securing themselves against against the L1. In the case of ZK, we're back to costly. It's incredibly costly to provide very sophisticated ZK proofs of very substantial state transitions. In the case of optimistic rollups, they're just very slow. 7 to 14 day time for verification, which essentially means you've got that same time for messages to get between the shards. Patchy in that each of the rollups supports different things. Each have their advantages. Now you can say, well, this is like a market and it allows innovation to happen, which is kind of true, but then it also means that interoperability is hard. It's not a standard platform that you necessarily you could build across. You kind of have to choose which one of the L2s you want to build into. And in the case of ZK, it's also centralizing because the economic model for producing proofs essentially is a winner takes all. If you look at bridge chains, Cosmos being a notable example, they're either insecure or they're very costly. They're insecure if they actually, if they're dividing Polka method of securing, so if each has to secure themselves, you're effectively dividing that capital, which is underwriting the security of the state transition, or the security of non-reversion. Or they're costly in the case that you are not doing any clever roll-up thing like Polkadot does, and you're just, I think, or they say replicated security, where you're essentially using the same validators to validate every chain in turn. Furthermore, you've still got persistent state partitioning, which leads to the inability to synchronous networks. And then in the case of the high-performance synchronous networks, Solana being a good example, generally less resilient, generally limited in terms of scale to whatever the fastest node on the network is. And since not all nodes will be able to match the fastest node on the network or the amount of capital underwriting it, it tends to be centralized. Right, so let's get back to Jam. So Jam intends to scale and increase its performance through relaxing, but not totally removing coherency. This is the sort of key innovation, if you like. Coherency is relaxed just a little bit, but we still want to maintain a fairly substantial amount of coherency. Enough that applications written on Jam can, or maybe applications written on a service on Jam, feel as though they have a level of coherency more or less equivalent to a single synchronous, fully coherent system. So we call it generally coherent. With transient decoherence. So with decoherence that sort of pops in and out, but then sort of resolves itself very quickly. Jam is based on this concept of core, many cores, 341 in the current protocol. And a portion of the computation is done in core. This is the bulk of the computation. It's where most of the heavy lifting happens. And then a portion, a much smaller portion, is done on chain. And this is the bit that needs to be actually synchronous, actually have sort of immediate finality, set almost immediate finality, and actually be stateful. And by combining these, you end up with the ability to perform a significant amount of performance, a significant amount of computation and data access, while still having this this ability to sort of be able to finalize and have a stateful system. In some sense, you can think of this as a transactional database portion, where you can kind of put small bits of code, you can deploy small pieces of code and have it sort of read and write from a database. Yeah. The chain is, if you like, that kind of database. And then this is actually where you do all of your computation. kind of think of it in that way. That might be a sort of more helpful way. So, basis of coherency is a service, and a service has these two portions to them, two pieces of code, refine and accumulate. And the refine part happens in core, and the accumulate part happens on chain. So you kind of take some data in, do some refining on it, yield some data out, and then you can also send some data, send some instructions, if you like, sort of into the database for it to read and write in the database. And once it reads and writes in the database, then it's like done, it's settled. That bit is atomic. Because the distributed decentralized data lake, so this very large, if you like, kind of shared hard disk, sits between all cores, you end up with the ability to transfer data between cores in a kind of transparent fashion. It's almost like on a CPU, you might have two threads or two processes operating in different CPU cores, but it's a shared memory. Okay. So if one writes data into memory, the other one can read it more or less immediately afterwards. Yeah, this can like happen through whatever IPC channels, shared memory channels. Sort of the same here. You have this DDL, decentralized data lake, is sort of the shared memory, or the shared hard disk. And different services, or the same service, potentially different services, can write data in to the data or yield data into the data lake. Other ones can read that data more or less immediately afterwards. That's the kind of clever bit. And that's what makes Jam generally coherent, because it has this kind of memory, this shared memory, that is mostly coherent. Yeah. In that these services can sort of export data into this shared memory, this data lake, and also import it back from the data. Yeah. Yeah. And then we can also do data lookups for data that doesn't change very much. This is useful for things like code blobs, where you want to upload a code blob, and you know it's not going to change for a week or two at least. It's more expensive than putting data into the distributed data lake, but it's always available immediately. So you can think of Jam as a roll-up host and reactor. What I mean by a reactor, basically, build a reactor is something that kind of has the ability to take these several data sources and bring them together, and then make them coherent. And a roll-up host essentially is a parallelized, secure parallelized processing environment. So Jam hosts 341 at the moment, according to the design, secure rollups, along with a reactor that can take the outputs of these rollups and build them into a coherent world model, which sits actually on the Jam chain. You can look at the rollups rather than as a kind of reactor preprocessor, but a preprocessor that also has access to this distributed data lake, which in some senses is stateful, right? So it can output data into the distributed data lake and take data back again, but it's not super coherent. So it's sort of it's a mostly coherent system. The actually coherent system is the on-chain state. That's known and everywhere. So it's a little bit, this is why Jam is a mostly coherent system. There's data lake that's synchronized every 1 or 2, right? So this is the level of sort of transience of incoherence. On the same core, the data lake is essentially always synchronized. But if another Jam core wants to import data that the core has exported in the past, it might take 1 or 2 blocks for it to be able to do that. So you have this kind of story, which is not especially dissimilar to the reduced coherency that a multi-core CPU or a multi-CPU board would have when looking, when trying to read and write from the main RAM. Yeah, it's like they have like levels of cache. They'll have like write through cache, and then it might be that one of the cores has some unwritten changes to some memory, and before some other core can read that memory, it has to write those changes out so that when that other core reads the memory, it will read the right data in. Yeah, and this like reduced coherency is just a necessary part of scaling a system, of having multiple cores, multiple CPUs. Yeah. And it's sort of the same with Java. So we're trying to build a machine that kind of mostly looks like it's a single coherent machine, but in reality, there are these slight relaxations of the rules. And these relaxations lead to certain situations where things will go a little bit slower depending on which core you do the operation. Yeah, in terms of its security and consensus, it's basically reusing Polkadot relay chains technology, so ELVs, which I've kind of named cynical rollups because they're kind of like optimistic rollups, but they're much more efficient. And Safrol. Actually, Safrol isn't on the relay chain. So Safrol is like a slight simplification of the Sassafras consensus, like block production mechanism, which is, I think, slowly being rolled out to parachains. And then Grandpa is being used unchanged as the finality mechanism. Okay, so like going back to like what does it mean, this like semi-coherent, mostly coherent, transient decoherent? Basically you've got this is jam, the big outer circle is like the whole of jam, and then this outer ring is the not entirely coherent kind of part of jam, and it's a lot more powerful than the inner circle, which is the actually coherent part of jam. Yeah, the not entirely coherent part of jam is like a 341 core CPU that can process, in excess of half a gigabyte a second of data, has 1.6 petabytes of storage, right? It's a serious piece of compute hardware, yeah? But it's not entirely coherent, which essentially means that two services might not see exactly the same thing at any given time. Yeah.
Can you elaborate a bit on the relation between services, what you term here roll-ups, and cores?
Roll-ups are a more industry-wide term for how we implement cores. A core is a conceptual atom of a virtual compute hardware. Basically, it's the virtual equivalent of a CPU core. What was the other one?
Services. How services map onto cores? Like
services are basically processes. Are they basically processes? Yes, they're basically processes. So like they are the software that runs on these cores. It's not quite as simple as thinking of them as processes, because services can have can be run on multiple cores at the same time. But from the perspective of the service, it doesn't really matter. When a service is run on multiple cores at the same time, it will eventually be make its way into this fully coherent reactor portion, and then that will just get all of the outputs from this in one sort of big array, and it can decide what order everything happens. Like there isn't a particular order, right? the ordering essentially gets set when it comes in here. Before it comes in here, they just, you know, there is no obvious way of ordering them because when they come in, they might pass through this outer ring at different speeds, or they might all pass through at the same time, at exactly the same time. It's like, well, how do you order that? What if one comes in earlier, takes 3 blocks to get through, and then ends up in here, and one comes one block later, and only takes 1 block to get through and ends in here? Do you then keep, like, it's not an easy question to answer. Now you can force ordering now with one of the later changes to the protocol, ordered accumulation, and be certain that these pieces of computation will be seen by the reactor in a particular order. But you don't need to do that if you don't want to do that, and if you don't do that, it's going to get into the reactor faster. So it's generally better to. And this is again a little bit equivalent. Or it has some similarities to memory access fencing on when you're doing like low-level CPU programming and with shared memory. And you can like basically say, I don't care what order this actually happens in memory, or you can say, I really care. You know, basically stall the CPU until everything else is finished with this bit of memory, and then process my thing. Yeah. So yeah, you've got this outer bit which is not entirely coherent, not entirely ordered, right? And then you've got the inner bit, which is where the ordering happens and the final changes are made onto the chain. And it's by breaking this down, because most of the time, like if you look in other systems, it's only got this inner bit. It hasn't got the outer bit. Yeah? And it's the outer bit that gives us so much more computation power. It allows us to do so much more impressive things. Okay, so if we look at the topology, we can imagine cores as these funny shapes here. With this bit being the bit that is not entirely coherent, and this bit, the smaller bit, being the bit that is coherent, that happens on chain. So this is the bit that happens on chain, this is the bit that happens in core, if you like. And so, because all of the things that happen on chain happen at the sort of same time in the same place, that's why they're kind of overlaid in the middle. Whereas the cores happen largely independently of each other, so they're on the outside. But from time to time, like this is time going down, so this is every block basically, every time slot, every 6 seconds in the case of that. They can read and write sort of into this distributed data lake, and therefore by exporting into the data lake, importing in a later block, they are effectively transferring information from a previous time to a later time. And because they all share the data lake, it's not fixed into one of these cores, but it can move between cores, or even spread out among cores, or be merged from multiple different cores in the past into one core. So you can see, for example, here, it's got a blue one coming from this core, and a yellow one coming from that core. It's going into the same core. And that's fine, not a problem. I don't know, here, maybe there's like a pink one coming from wherever, and another pink one coming from there. It's meant to illustrate the fact that they can essentially draw information from essentially any point in the past, maybe like up to a month, and from any output, any exporting cores. Yeah? It's all kind of part of the same data lake. It's all part of the same shared memory or shared hard disk. And that's the clever thing, because it's all the input is being drawn from the same overall system, or same overall kind of data lake, data pool. It's coherent. It's a coherent machine. If these cores could only draw from their own cores shared like memory, then it'd be much harder to get information from this guy to this guy, yeah, in a later time. Yeah? And that then we're back into like the parachain model, and we're back into the persistently partitioned state. And that's, as I say, that's a bit of an issue. Good. So, yes, shared states are arranged into services. These are basically kind of applications. Services have a single piece of code, 3 entry points, refine, accumulate, and transfer. On transfer is the easiest. That just accepts some memo or tokens from other services, does something with them, whatever it is, it doesn't really matter. It doesn't care from the point of transfer. Refine is the thing that does the heavy lifting, the read and write to the distributed data lake. Accumulate is the thing that integrates the output of this into the shared state, into the world model, the coherent world model of the chain. Jam's permissionless, the services that they're hosted on the Jam chain. Putting in a new service is a permissionless operation. Anyone can do it, you just have to pay the money. They're limited only by the deposit that you put. And one example, just in case you want something in your head as to what a service might be, well, Polkadot 1 would be a Jam service. Like the whole relay chain thing would be a Jam service. So these things are pretty powerful. Jam doesn't do transactions. It's not meant for direct user interaction. It does have data that is fed in from the outside world, but it's fed in. Basically, this is just the opinion of validators. Yeah. So we're only interested in kind of what validators think. We're not interested in what anyone else thinks. So guarantees are essentially what each of the validators is, in some sense, guaranteeing happened on a particular call. And they're kind of saying this call was doing this thing at this time, and if the result is invalid, you can slash me. So they're guaranteeing the result is a particular. Assurances are data in terms of data availability. It's basically a validator saying, I have made this data available. I assure you the data is available. At least my bit of the data is available. Disputes are in case one of these guys does something wrong. Well, not this one really, but this one. In case that any of these guarantees are invalid, validators can vote on the guarantee being invalid, and if it's invalid, they essentially vote to slash the guarantor who is signing that it's valid. Pre-images are, as I was mentioning earlier, things like code blobs that don't change very much. Pre-images are feeding this data in. And tickets are an important element of this cipherable block production protocol. In all cases, we try to minimize opinionation as to how these things work. And one of the ways of minimizing opinionation is by putting it into maths and really trying to simplify it. Jam doesn't care about any of this stuff. It's not interested. Yeah. So this stuff is, as far as Jam protocol is concerned, high-level things that will be implemented on a service that sits on Jam. Jam basically just provides hooks for these things. Yeah. It doesn't care about how they're actually implemented. So Jam services, they have data, they have code. In that sense, they're a bit like they sit on chain, so they're a bit like smart contracts. They're a little bit different to smart contracts in that their computation is kind of pipelined with this refine, accumulate, on transfer pipeline. With some of the computation, happening in core, in this non-coherent model, or not so coherent model, and some of it happening on chain in a coherent model. They do not, you don't purchase gas for running a service, at least not for running a particular transaction in a service, really. Rather, you kind of rent a core. Right? You rent a core, and then with this core, you can push a work package through the core which can do something to a service. So there's like a little bit of it's a little bit more built for higher throughput than having to pay for small amounts of computation. You buy a core, it's the principle you buy. You might buy a core, you might then split it up and all of the stuff with agile core time, and then actually end up only buying on the secondary market a fraction of a core. But in any case, you're we're dealing with much a coarser grain of computation resource than like paying for individual gas. And overall, services are asynchronous, right? So the block that the atom of work that a service does is not a transaction, it's a work package. It's actually a work item, one of the items inside of the work package. And these work items, because they're pipelined, because you have some heavy lifting that happens in core, then some consolidation into the chain that happens on chain, and then potentially someone transfers stuff, if there are any transfers that come into it. That computation happens sort of in an asynchronous fashion, right? It will happen a block or two before you really see the effects on chain. And as such, that has a sort of slight difference in how you might think about jam services compared to smart contracts. Like, essentially, you'll feel the effects on chain, but later you realize if it was. So yeah, the service pipeline, as I mentioned these three parts. There's actually an authorization portion as well, which is to check that the work package that the service is being invoked by is authorized to run on the core that it's supposedly going to be run on. I'm not going to go too much into the authorization. So the refine, we've got some numbers here, until we actually do the prototyping, take it with a pinch of salt. But roughly speaking, refine is expected to accept around 12 megs of data per 6-second work package time slot, so 2 megabytes per second. And this is a combination of extrinsic data, so data that we're pushing into the system, and data taken from the distributed decentralized data lake. Still, 2 megabytes a second is a very substantial amount, and that's per core, right? Jam has hundreds of cores. It yields up to 48 kilobytes of data. If you like, this is the consolidated instructions that will go into that database, right? That shared database. Accumulate. It can execute for 5 to 6 seconds of PVM gas. PVM gas is pretty efficient compared to, like, for example, EVM. You can get quite a lot of computation in your 5 or 6 seconds. There has some contextual information on what else the work package has in it. Because if you remember, when a service starts doing something, like refining something, it means there's a work item which mentions this service, that is in a work package that is being executed on a core. A work package can have many work items, which means you could in principle have one work item for one service, another work item for another service. Now they can look to see what each one is doing, which opens up the possibility of essentially doing cooperation between two different services if they're co-scheduled in the same work. This is an interesting possibility, because then it means you can do maybe 2 different parachains and essentially know that at this particular time that parachain was doing this thing and this parachain was doing. They can each know what each other was doing and be certain that if one is getting accumulated, the other will be getting accumulated, and vice versa. They can do things like look at pre-images and invoke PVM instances. This invocation of PVM instances is very, very important for doing things like parachecks, because it means that a service can create a whole new virtual machine, kind of in a kind of hypervisor environment, if you like. Yeah, so you can kind of just create a new machine with nothing in it, put stuff in its memory, put some code in it, and then set it off and give it some gas, see how far it gets, and then basically look at its memory after it's finished executing, maybe after the gas has run out or when something else has halted it, and potentially suspend it, save everything, and then resume in the later block. In theory, this is totally viable, and it's been designed so it's viable. And this allows us to do all sorts of more sophisticated models of actors, smart contracts, much more sophisticated than classic.
Thank you. Can you remind me what the PVM is?
It's the Polkadot Poker virtual machine. So it's a VM. It's similar to the RISC-V instruction set, but it's been optimized for our needs. Inside of Accumulate, basically this is a optimized Turing-complete database interface, right? So you you deploy PVM code to be your Accumulate code for your service, and it has access to this shared database. So it can read other services' storage, and it can write its own services storage. And it takes these 48 kilobytes of data to do whatever it needs to do with this database. Essentially, it can record information that is useful, that it needs to be recorded in a coherent fashion. And it might be that two different 48 kilobyte pieces of data come in that are in some way mutually exclusive. For example, it could be a parachain that has two new child blocks, so it's a 4-go parachain. Yeah. And they might both be trying to say, well, you know, Asset Hub actually has block 42 is this, and then on the other side, another refine might come in that says actually block 42 is that. Right? And we have to choose one block 42. Well, that selection of one of those two would be in the accumulator. It's the thing that actually figures out what the eventual state is. If everything is synchronous, everything is sequential, you wouldn't need to do it. Accumulate would just be getting everything in some order, and it would. I guess the first one that comes in, it would just say, right, that's the block 42, and it would ignore the second candidate, right? In this case, it's asynchronous, and so they both go into refine, or at least in principle, they might both go into refine. Refine doesn't know that the other one is around, and so they might both get through refine and into accumulate, and then it's only at accumulate everything, that the whole thing is known, the world is known, and that's where the decision is made as to which one to keep, or maybe neither, maybe it throws them both out, I don't know, but it's like this logic that figures that out. And then finally on transfer, which deals with any of the messages coming from other services. Here is a little kind of diagram I tried to do. So basically, new data might come in. You might also take in some past data from the past month. And these two must total no more than 2 megs a second. And then you might also export some data into the distributed data lake for access for the next month. And that together with the new data must, actually this line doesn't exist anymore. It's just the memory. That must total no more than 2 megabytes. The pre-image store up there. You have some pretty hefty numbers for the amount of EVM gas per second. In this case, per core, we're looking at somewhere around, I don't know, maybe a billion EVM gas per second. Maybe a bit more. Maybe it's like 2 billion. it's kind of hard to compare PVM gas to EVM gas because they're very different virtual machine models. But our initial calculations of trying to sort of recompile EVM code into PVM code suggests these kinds of numbers. And then, as I said, there's like an 8 kilobyte a second, 48 kilobytes per 6 seconds, a sort of little data pipeline into the on-chain portion, the accumulate portion, and this is the bit that does the database access. And roughly about 1 million IOPS a second is what we're looking to achieve across all services. Right? So divide that by 341 if you want the number of IOPS per core. And then per core, around 1.5 million-ish EVM gas per second. To compare that to Ethereum at present on the L1, it has about 1-ish million gas per second. But that's our 1.5 million is per core. In total, we're looking at about 500 million across all 300 cores. And that's only the kind of database bit of it, right? That's only the on-chain portion. The in-core portion is much larger.
What does the 60% stand for the accumulate stage? 60% PVM?
60% of the sort of native speed of PVM. The reason it's only 60% is because we, whereas here, it's sort of 100% PVM, because we can probably basically keep all of the cores going at full pelt all the time because they're asynchronous. This bit is synchronized, right? Which means if you can't keep it going at full like kind of temporal saturation because you need time to share the blocks, reset everything, do other stuff in the state transition.
Same as in Polkadot right now, really change your 3 seconds of the 6 seconds that you can use for execution.
Yeah, I think.
Or like
No, I think it's even worse. I think in Polkadot it's like 1 second or something.
Why does it say 25 to 50% on the left then?
This is of native x86.
Ah, got it.
So PVM roughly runs at 25 to 50% of native x86. And then this is 60% of that. But I mean, the fact that we're comparing it to native x86 at all already puts it in a, vaguely in the same order of magnitude, already puts it in just a league above current blockchain execution technologies. Right? It's now the thing that might take this down, like we can make it run at 50% of native x86. That's not a big issue. The issue is that whether we can make it run with secure gas metering at 50%, right? Because it means that all possible code that is written has to all run across the board at 50%. And the thing is, it's quite easy to write some code that will be pessimized. Yeah, that will run quite a lot slower. So we have to like kind of work out how good our gas metering can be, how secure our gas metering can be, so that no matter how pessimistic your code is, the gas that's charged won't be significantly lower than the time it takes to actually execute. And this is the hard bit. It's particularly hard for memory accessing. Like if you just write code that kills the cache, that just like basically randomly reads from memory, you can make everything go 2 orders of magnitude slower than it should. As if you were just reading from the same or whatever 100K of memory. Now the trick that we're going to try out, we haven't tried it yet, is to basically have a gas charge multiplier that gets bigger the more memory you have access to. So if you have lots of memory allocated and ready to read from, your charge multiplier, you're basically going to burn through 10 times the amount of gas as if you only have a very small amount of memory that you could read and write to without a fault happening. And hopefully this will give us some degree of secure but still high performance gas metering. Like not the gas metering itself, but like gas schedule. So your gas costs, your gas prices have to be in line with the most pessimized code that anyone can write. They have to be in line with the time it takes for the most pessimized code that anyone can write to actually execute. And that's the tricky bit. Like actually making the VM execute fast isn't so tricky. Making it execute fast in all circumstances is tricky. Okay. Right, so yes, jam cores. The work on jam cores are work packages. A work package executes for 6 seconds on a jam core, more or less. Not more, maybe less. And they may be going to be about 12 megabytes big. Once the refine part happens, it yields 48 kilobyte sort of intermediate output, which then makes its way into the accumulate stage, which executes on chain. There is a authorization mechanism, which I'm not going to go into, it's a bit technical. But basically, this is the thing that Agile core time plugs into to make sure that only the work packages that the owner of the core time wants executing are able to be executed. And just as Agile core time is sold in monthly chunks on Polkadot relay chain, so it will be on Polkadot jam chain. And just again, in the same way, those chunks can be subdivided, straddled, and resold. Good. Hopefully that was a reasonable introduction.
Thanks, Gab. Okay, we're gonna have a round of 30 minutes where I will invite the Jam team members to talk a little bit about their projects. So something around 10 minutes per team, can be a little bit more, a little bit less, but not that much. And then we can have a round of question and answers. If you want to take like 5 minutes for a break, maybe it would be a good idea to have a break, and then we come back with this and you can take t-shirts and gray paper printed version here. Everybody is welcome to. Oh, my God. Sorry, boss. It's too long. It's too long today.